Right now, if you want to benchmark an AI security agent, you give it a 1,000,000 token budget, unlimited tool calls, and a capture the flag challenge. You measure peak success. But in a real security operations center, or even a professional red team, every single reasoning step, telemetry query, and enrichment call costs money. So how do we actually measure whether these agents are operationally useful, rather than just academically impressive? A new study from Kassianik, Nelson, and Singer cuts through the noise by introducing a cost-aware evaluation framework. Instead of asking what's the maximum score an agent can get, they ask, what capability does a model actually buy per dollar of inference and tooling? They run a direct comparison across offensive Cybench challenges and defensive Splunk BOTS V1 investigations, and the results reveal something fundamental. Offensive and defensive security, agents scale in completely different ways. Let's break down how they actually measured this. The team uses a shared evaluation harness built on a RAAC-style agent loop, which chains reasoning steps directly into tool execution. They pair this with auto-compaction to manage context windows efficiently, triggering a summary or provider-native compression when the context hits 90% of the limit. Between offensive and defensive tasks, the only thing that changes is the tool suite. For offense, they use Cybench, a sandbox CTF suite with Shell and Python access, where agents hunt for hidden flag tokens. For defense, they use Splunk BOTS V1, which simulates a real SOC investigation. Agents get Splunk telemetry, search tools, and limited external enrichment like VirusTotal and WHOIS, but they're graded on a sequential, point-based system with hint penalties. Crucially, they implement strict cost accounting. Every run is capped at a fixed budget, and they track model token spend separately from priced tool calls. They also use retrospective budget caps. Instead of just running new tests at different prices, they replay completed traces under tighter budget constraints to see exactly where performance drops. This isolates the model's actual reasoning headroom from the noise of comparing completely different runs. Let's start with offense. Cybench results show a clear linear scaling regime. When you give the model more test time compute, it solves more challenges. GPT-5.5 dominates early, solving over 94% of challenges at just over $1 per solved equivalent. But the real story is in the budget headroom. When they replay traces under a tighter 80-cent cap, Claude Opus 4.8 and DeepSeek V4 Flash still show significant performance drops, proving they have deep reasoning headroom. Conversely, GPT-5.5 already solves most challenges well below that threshold. There's also a notable policy layer. Several GPT-5.6 variants and Claude Fable 5 hit content filters or refusal limits, which artificially caps their offensive scores. But purely on capability, offensive security is a compute game. More budget buys longer sandbox exploration, more command retries, and a higher chance of recovering from false starts. Now switch to defense. BOTS V1 tells a completely different story. In a SOC, success isn't about raw reasoning budget. It's about disciplined tool use, telemetry navigation, and knowing exactly when to pay for enrichment. The data proves it. Claude Opus 4.8 takes the top spot, scoring 93.9% of the points, while spending just under $3 per 1,000 points. It does this with highly selective tool use, averaging around 600 tool calls across the entire investigation. Compare that to DeepSeek V4 Flash. When you double its budget from $2 to $4, its score barely moves, but its tool calls jump from 4,400 to nearly 5,000. It's burning budget on redundant Splunk queries and enrichment calls after it's already missed the key field. The scaling curve for defense doesn't climb with spend. It plateaus, and often, higher spend correlates with lower efficiency. Defensive agents need precision, not volume. But there's a critical caveat with public benchmarks, especially BOTS V1. The dataset is old and public, which means model contamination is a real risk. The researchers ran a strict no-tools probe, stripping away Splunk, Bash, and external APIs, and just asked the models to answer from context and prior knowledge. The results were eye-opening. Even without tools, Claude Opus 4.8 scored nearly 75%, and GPT-5.5 scored over 60%. This isn't to say the benchmark is useless. It's a highly reproducible harness. But it proves that absolute scores on public SOC benchmarks require decontamination checks before they're treated as evidence of live investigation skill. You can't just look at the final point total and assume the model actually analyzed the telemetry. So what's the bottom line for AI security evaluation? First, cost-aware metrics are non-negotiable. Peak success rates are academically interesting, but operationally misleading. Second, offensive and defensive tasks have fundamentally different scaling laws. Red teaming rewards compute and iteration. Blue teaming rewards telemetry literacy, tool discipline, and economic efficiency. And third, public benchmarks need contamination controls built into their evaluation pipeline. As we deploy these agents into real SOC workflows and penetration testing environments, we need to stop measuring them like they're solving puzzles in a vacuum and start measuring them like they're running in production. The models that win won't just be the ones that can reason the longest. They'll be the ones that know exactly when to stop, when to query, and how to deliver analyst-grade answers under a budget. If you want to dive into the full methodology, the bootstrap intervals, and the interactive scaling curves, the link is in the description. Thanks for watching.